Tonight on Applied Science, we're going to talk about electroluminescent spray paint that lets you put an electroluminescent display on any curved or even flexible surface. And then also I'm going to show you a custom driver circuit that I designed that lets you get really smooth animations with your newly created electroluminescent device. The electroluminescent paint is a commercial product called Lumalure. And when you buy it, it's sold in this kit of different layers. And what you do is spray these things down sequentially to make a display. So the kit includes everything you need except for a way to deposit the paint. And generally, I've been using a little airbrush like this. This one's called a Neo. It's about $40 or $50 on Amazon. But you can also use this cheapo Harbor Freight one. The difference is that this is sort of a siphon feed, and this is sort of a gravity feed, and the gravity feed cup is very small. So if you're doing very small objects, it's helpful to have a really tiny airbrush so you don't waste paint. This stuff is very expensive. It's about $450 or $500 for the set of paint. And it sounds bad, but if you're doing small displays, this amount of paint will last you quite a bit. I don't know what the coverage is exactly, but I've been making all kinds of different test panels, and you can easily spray something this big with the airbrush, and it only uses, a 50th or less of your bottle. Lumalure is targeted for the automotive industry, and this company actually has quite a few good tutorial videos, so I'm not going to rehash the whole thing, but I am going to add what I've learned from it and also step through it quickly just so you can see. The trick is, if you want to make a pattern like this, like if you actually want the light up area to be a pattern, the easiest way to do that is to use a vinyl cutter. And so the trick is that you load this vinyl into the cutter, cut out the section that you want to light up, and then use a transfer sticker to move the vinyl onto your substrate, and then spray the copper paint, which is the first step of this Lumalure process, through the vinyl cut thing. So you end up with the copper patterned where you want the light to come out. I've tried patterning every other part of this whole Lumalure process and found that patterning the copper is by far the easiest way to control how the light comes out. After the copper paint is fully dry, what you want to use is a little 1000 grit sandpaper to make sure there's no bumps sticking up. I've noticed that the most common failure mode for this whole Lumalure system is that there's a bump, either a dust particle or a hair or a little bit of crust left over from where you had a tape line where the paint kind of wicks up to the edge of the tape. What this does is create a puncture point through the dielectric layer and shorts out your whole panel. So you always want to be sure that you're dust free, and if you notice some kind of a bump, you have to get some sandpaper in there and smooth it down and then repaint to make sure that there's no puncturing through the dielectric. After everything is nice and smooth, you can spray the dielectric on, and this is more than just an insulator. Don't think that this is just that the sole purpose of this layer is just to keep the things electrically isolated. The purpose is actually to create a tiny capacitor in there. So the way electroluminescence works is it's basically like a leaky capacitor, and every time you charge and discharge the capacitor, some of that energy goes into creating light. So if your capacitor is no good to begin with because it doesn't have a high dielectric constant, then you don't get very much light out. In fact, it doesn't really work at all. So the dielectric constant of the stuff that's in this special paint is quite high. It's barium titanate is the powder that's in there, and that's commonly used in all kinds of ceramic capacitors. The next step is to spray a phosphor, and there are about 8 different colors available. You can even mix and match them in the same panel, which is pretty nice. Some are a lot brighter than others, so this orange color is not particularly bright. The green, I think, is one of the brightest ones they've got, so you can kind of see the difference in light output here. And then after the phosphor is dry, we want to apply a clear conductive electrode to the top so that we can get light out of this whole stack up. And the trick is there's this special material, P.PSS, which is an acronym for polyethylene dioxythiophene polystyrene sulfonate, I believe. So it's an intimidating name, but it's actually a very easy to use material. You just spray it on and let it dry, and you've got a conductive clear electrode. Pretty nice. And the electrical resistance is surprisingly low. It's comparable to an ITO film, but this is nice because you can spray it on with an airbrush, and as it dries, it becomes conductive, and so you get this really cool effect when it's drying, you can use the heat gun to kind of accelerate it. It becomes conductive and sort of creates the display as it's drying, which is quite nice. In order to attach your electrical connections to the panel that you just made, Lumalure recommends like JB Weld or something. I kind of prefer using this conductive tape made by 3M. And so the adhesive in this tape has little particles of metal in there that pierce through the adhesive. So when you stick it down like this, it makes a conductive bond to the surface, and the adhesive is not particularly aggressive. It's kind of like a Post-it note. I mean, a little bit stronger than that, but it's not crazy. So you can pull the tape off and put it back on, and it's a very low resistance connection. It's totally fine for what we're doing. You can also solder a wire onto the tape before you've applied it and then stick the tape on so that you don't expose your panel to anything high heat. Works great for these really thin substrates like the printer transparencies too. I've also noticed that I can touch the top layer. I was going to say, I've noticed I can touch the top layer without getting shocked, but I actually kind of did get shocked that time a little bit. That's actually the first time I've gotten shocked off of this system. But anyway, I can hang on to it like this and I'm not getting shocked now. I must have just hit just the wrong spot. But in theory, the clear conductive electrode is charged up over here. So if you manage to touch both of these, you'll definitely get a shock from it. I've applied this paint to all kinds of different objects, 3D printed objects, this flexible printer transparency stuff, even painted metal parts are okay. Even paper, actually, although the paper was kind of pushing it. This was like glossy inkjet paper, and it worked okay. The biggest problem I was having is that the masking tape was actually ripping the paper apart. But it held the paint okay, and the end result was not bad. Let's talk about the electrical side of this. The Lumalure kit comes with a couple of these little inverters, which are pretty standard for driving EL wire and EL panels. But these things have a couple of problems. One is that they're only on or off, like there's no dimming. Some of them will dim, so you can flash it, and it's a little bit dimmer now, but there's no programmatic control of this thing. And the other problem is, I'll put the microphone close so that you can hear it, they all whistle annoyingly. So I wanted to come up with a better circuit that would allow dimming of the EL panel, really rapid control for sequencing, like lots of channels, no annoying whistling, and as much other stuff as I can pack in. So let me show you the circuit that I created to drive all these EL devices. Okay, here's the board. Let's start at the lower left here. We've got a pair of LDOs, a 3.3 and a 5 volt LDO. The 5 volts is required by the high voltage switching chip, which we'll talk about. You could also supply the 5 volt with a boost converter or a buck converter or something else, but I just went with LDOs. The control part of it, like this whole area in here, is basically an Adafruit Trinket M0. In fact, that's where I get the parts to build all this. So the button, the capacitors, the AT-SAMD21 microcontroller, even the LEDs and the current limiting resistors are removed from the Trinket, which makes it kind of convenient because the chip is already programmed with the bootloader and the footprints are already in the board CAD program and everything, so that's great. And also Adafruit is great, and you can use some of the firmware that they've created, which is very helpful. Also, the way that the high voltage is created on this board is these pair of high voltage circuits that run in parallel. And the one on the left I've marked as optional, OPT, because you don't really need both of them. If you're not doing a high power board, you can actually just have one of these. Or if you were doing a mod to this board, you could add more channels and get more total power out of it. The chip that runs this high voltage supply is an LT3468, which is a driver for a transformer, and the transformer is actually this tiny little thing here. It's actually the smallest transformer I've ever seen. One of the other goals for creating this circuit was to make the board height as low as possible. So the USB connector and this big capacitor up here are the tallest components by far. Otherwise, everything is under about 2.5 millimeters. So this LT3468 is designed to run the transformer in flyback mode and generate a high voltage. And the chip is pretty trick. It actually has a voltage sensing circuit in there as well, and it actually senses the secondary voltage by monitoring the inductive kickback on the primary, which is pretty cool. Unfortunately, it has a fixed voltage, so I think it charges up to like 300 volts, which is great, but it's actually too much for this EL driver, which has a limit of about 200 or 250, I think. And so what we do instead is actually use the MCU to monitor the high voltage and turn on and off the high voltage regulator very rapidly so that we kind of cycle, sort of duty cycle the high voltage supply. And this is actually a benefit because the firmware can control the supply voltage at will. You can even adjust it mid-program if you want, which is great because then you can change the overall brightness of your EL panels. And if you have a really small EL panel, you can jack the voltage way up to get high brightness. And if you have a really large EL panel, you can turn the voltage down so that you don't exceed the maximum current ability of the circuit. The circuit board is designed to accept one of two different high voltage switching chips. One of them is the HV513, which is here, and this has 8 channels of high voltage output. And the other chip is an HV507, which has 64 channels of high voltage output. And they both work about the same. It's basically just a shift register. And so we shift in either 1 byte or 8 bytes of data. And the high voltage chip will basically just display that data in parallel on all the output pins. I'll describe my circuit board build process briefly. I use a little tiny ceramic heater on an insulator tile that I got from Amazon, and I'll put links to all this stuff in the description. And for boards that are small enough to fit on here, this works great because I use the bench supply to power it, and you can put a very precise amount of power through the heater. To dispense the solder paste, I prefer to use this pneumatic foot pedal controlled dispenser. And so I've got a 3cc syringe with a really tiny plastic nozzle here. This is the smallest nozzle that McMaster sells. I think it's a 27 gauge, and it's T5 solder paste. And I find that when I get just the right amount of coffee, I can do a 400 micron pitch QFN footprint with this manually, just hand holding it. It usually comes out pretty well. And then reflow, fine. Sometimes I even use a little hot air from the top at the same time the hot plate is going, just to sort of control the process and make sure it's nice and even. Generally, this works really well. I should also point out that this PCB was designed for my laser-defined copper on plastic process, so that all the traces are really fat and the spacings are a bit bigger than I would do if I knew I was pushing a conventional circuit board to sort of the packing limit, basically. The circuit will control EL wire as well, and so I made this glove that I wore around Hackaday SuperCon, and it lasted all weekend, which was better than I thought. I actually stripped the plastic coating off the EL wire, so there's still an inner plastic coating, so they're still insulated, but there's no colored outside on it, so it's just like the core of the EL wire. And there's 32 EL wires here using the 64 channels from this high voltage shift register chip, and I'm using them in pairs. And so the way that EL works is that it's a capacitor basically, and you want to deliver a square wave to each one of these capacitors, and every time you flip polarity on the square wave, you get a pulse of light out. So the more rapidly you send a square wave to that EL wire, you get more light out of it. And so with the current speed that we can get, I can have about 64 grayscale control at 60 frames a second for each element, which is pretty good. Don't get too excited though. You can't drive like a 2-meter long EL wire with one of these outputs. Potentially on the 8-channel driver chip, you get more power because it's only 8 channels instead of 64. But with this one, if you put a 2-meter piece of wire on here, it won't light it up. And I haven't figured out exactly what the limit is. So it's more than 10 centimeters, but it's less than 2 meters. The power source for this thing is 6 AA batteries, and it lasts running this pattern about 3 or 4 hours, I think, or so on those 6 AA's. So it's not a very power efficient circuit. One 9-volt would not be enough to run this for very long at all. And you can see I've got heat sinks on here because it's really not that efficient, and those heat sinks are kind of more necessary than you might think. Depending how aggressive the lighting program is, you can run a whole lot more power than you would otherwise. Like if you're very conscious about your lighting program, you don't burn very much power. But if you turned all the segments on to full brightness, that would be way too much. The circuit can handle about 3 watts constantly, and it can peak up to maybe 7 or 8 watts but it can't dissipate that forever. And so if you ran it at 7 or 8 watts for 10 or 20 or 30 seconds, it would probably melt something. I also wrote a separate piece of firmware that transforms the outputs into a matrix driver. So instead of using the 64 or 8 channels in pairs and then flipping each pair on and off to control each segment, you can actually lay out all 32 in rows and columns and get this cool 32 by 32 matrix. Driving it, though, is pretty challenging because, like I said, every time you flip the polarity of any one of these electroluminescent capacitors, you get a flash of light. Well, this makes scanning through a matrix really difficult because you're constantly flipping something to address one pixel, and then inherently you kind of flip all the ones that you don't want to touch. So conventionally in an LED or even an incandescent matrix, you would put the state on the matrix and then hold it there for a while to let the light come out, so that your switch time is very low compared to your hold time, so you get a decent contrast out of it. But that doesn't work with electroluminescent because there is no hold time. You only get light out of the pixel when you're flipping its polarity, which if you flip it more rapidly, then you flip all the neighbors, and you can't, without a tri-state driver, I can't see of any way of making this work. However, you might be surprised how well it does work, and so I used Paul Stoffergen's great Octo WS2811 library to send some live video to the matrix. So let me cue it up. Okay, let's talk briefly about the firmware. This is written in Arduino, of course, because it's an Adafruit Trinket M0. I mean, the chip really is a Trinket M0, so everything, when you plug this into the USB, it's identified as a Trinket M0. You can control the voltage programmatically, which is here. You can tell the thing whether you're using the HV513 or the HV507 here. This max brightness is the number of grayscale levels that you'll have in your program. And if you change this, you'll get an automatic trade-off between frame rate and number of grayscale levels. So originally, I guess I had 63 here, and at 63 grayscale levels, you get 134 hertz refresh rate. So at 128, you'll get about half that. Still pretty good. It won't flicker as long as you're above about 75 hertz. There's a fair bit of manual register control in here because I really need detailed control over what these timers are doing. So there's two main timers that each fire an interrupt to get this thing to run. And the first one is a timer set up here that runs an interrupt which sends data to the shift register. So this is currently set up to run at about 8.5 kilohertz. So 8,500 times a second, the chip fires an interrupt and sends basically its frame buffer to the shift register. And that's pretty self-explanatory. The second timer setup is a little bit weird. It's actually set up as a one-shot, and what this does is it fires periodically, and if nothing re-triggers it, then it doesn't run anymore. And the point of this is that when this timer fires an interrupt, it will check the high voltage on that capacitor, and if it's too low, it turns on the high voltage supply. But what I want to happen is to have the high voltage be shut off if anything bad happens in the code. So if the processor halts for whatever reason, it can't just leave that high voltage control line in whatever state it was previously, because it might have been on. And if it leaves it on, it will cause damage to the hardware. So this is kind of a sensitive thing. So with the one-shot setup, the timer times out, and then if nothing happens, like if the processor is halted for some reason, it never runs the code to check if the high voltage is there, and hence never turns it on. That's the point of the one-shot. The main loop is where you actually program the graphics for this thing, and I have a whole bunch of commented out junk, but basically you can have delays in the main loop because all of the work is really being done by interrupts. So you can delay the code in the main loop and set the pixel values to whatever you want. The next step in developing this firmware would be adding like a graphics library or adapting Adafruits. Here's the interrupt handler that sends the data to the shift register. And this runs at about 8.5 kilohertz, and I measured it for a 20-second duration. So that's like 17% of the CPU time is spent in this interrupt, which is, I think it's pretty reasonable for this application. And the trick here is that every time you toggle a pair of lines going to an EL panel or wire, you get a flash of light out of it. So I have this loop that basically checks to see if the pixel value is, or if the current sort of iteration through all of the possible pixel values is less than the value that you want it to be. And if it is, then it toggles those two lines. And remember, a toggle means give me a flash of light. So fade step increments one by one as this loop runs, and eventually it will get higher than pixel values, whichever, I mean, let's say your pixel value is set to 50%. Halfway through this loop, fade step will get higher than the pixel value, and then it won't toggle that line anymore. So this thing basically steps through all of the possible brightness combinations and will light up only the pixels that are set to be higher than that cut point. Here's the interrupt handler that runs the high voltage setup, and it's important that we disable interrupts for this one because we really can't have any interruptions during this time here because it is pretty time sensitive. There's a quirk with that high voltage chip that I'm using. You can't pulse it too rapidly, so there's a minimum low time, which is why the loop is set up this way. I'm not going to really get into the hardcore details, but of course, if you have questions about this, contact me on Twitter, or put them in, or even better, put them in the comments, and then everyone can learn from it. Okay, see you next time. Bye.